Alright, hello and welcome to this quick walkthrough of the mini-test. Hopefully what you've done before starting this is had a look through your own script and had a think about some corrections first using the textbook in your notes. So just going straight to this walkthrough to copy the possible answers down is probably not the best way of doing it. Make sure you've gone through your own first and thought about any corrections, because this develops your ability to think and be resilient on the spot, is what a skill you'll need when you do the real thing. Okay, so assuming you've done that, let's get started. It says quite clearly that they want you to use oxidation numbers. So it says solutions of hydrogen peroxide are sold as disinfectants, and it says the concentration of a hydrogen peroxide solution can be determined by redox titration. Now you won't have done these before, but you don't need to have done them before, because it's not asking you to talk about redox titration. It's asking you to use oxidation numbers, which is what you have done before. So it's the same old story: which species has been oxidized and which has been reduced. So the first thing to do is obviously assign oxidation numbers to everything. So remembering that all the oxidation numbers have to add up to the overall charge, what I'm going to do is focus on each of the species, and then within each species see if I can work out the oxidation state of each element. So to help me, I'm going to remember the oxidation number rules. So something interesting to note in the oxidation state rules is that oxygen changes its oxidation state in one exception, and that's peroxides. So if you were to look at peroxides, you'll see that hydrogen peroxide has been mentioned. So we need to bear that in mind when we're assigning oxidation states. So if we now carefully look at what's changed in oxidation state, we can see that manganese has gone from +7 over to +2, which is a reduction because the oxidation state number has gone down. At the same time, oxygen has gone from -1 over to 0. -1 to 0 is an increase in oxidation number, so that's the oxidation. What's quite interesting is it's actually 3 marks, so you have to very clearly state what's going on. So you need to say the oxidation state that everything starts in, and in what substance it starts with that oxidation state, and then you need to say what's happened to it, has it been oxidized or reduced, and then finally what oxidation state it ends up as and in what. So let's go through that again. You start off by saying manganese has been reduced, so you've made a statement. Now you say what number it was to start with, +7, and in what substance was it +7, MnO4-. What does it end up as when it's reduced? It ends up as +5, and what substance is it in? MnO2. For oxygen, oxygen has been oxidized from -1 in H2O2 down to 0 in O2. Okay, so it says hydrogen peroxide can act as both an oxidizing agent or a reducing agent depending on the conditions of the reaction. So we're on part B now. In terms of electrons, I think that's probably the most important part of the question. In terms of electrons, what happens to an oxidizing agent? So be careful, think about what an oxidizing agent does. An oxidizing agent causes something else to be oxidized. So bearing in mind that an oxidizing agent removes electrons from something else, the oxidizing agent itself must gain electrons. Okay, so let's move the page up and do the next bit. Okay, so then it says a 10 centimetre cubed sample of hydrogen peroxide reacts with 20 centimetres cubed of 0.02 potassium manganate 7 when titrated. So to do this, we've got to bring the equation down a bit again. So a 10 centimetre cube sample of hydrogen peroxide. So I'm going back to my equation because I want to know the mole ratio. So 5 moles of H2O2 react with 2 moles of MnO4 minus. So the first thing you do is you work out the mole ratio from the equation, 2 to 5. Then you work out the moles of the thing you have all the information for, and that would be the manganate, because on the manganate you have concentration and you also have the volume. So that's what we're doing down here to get the moles. With the hydrogen peroxide, what you've got to do, because it's a 2 to 5 mole ratio, you take the number of moles of manganate that you've worked out and you multiply it by 5 over 2 to get the number of moles of hydrogen peroxide. So that gives you 1.0 times 10 to the minus 3 moles of hydrogen peroxide, which you can put into the N over V rearrangement of the concentration equation. Don't forget that the volume, 10 centimetres cubed, is going to be that one there, and that gives you the final concentration. So remember, the volume was given in centimetres cubed, wasn't it? So that means it must be divided by 1,000 to convert to decimeters cubed, hence why I've used 0.01. So let's move on to the next part. So finally it says, easily decomposes into water and oxygen. Hydrogen peroxide easily decomposes into water and oxygen. So it asks you to suggest why highly concentrated solutions of hydrogen peroxide are kept in dark brown bottles rather than the standard colourless bottles. So if it's kept in a dark brown bottle, that must mean that something to do with light affects that reaction. It might speed it up. Light tends to provide energy, doesn't it? So you've probably heard of free radical substitution being initiated by light. Now this is not saying that this is a free radical substitution, it's obviously not. But it could mean that more than one type of reaction might be catalyzed or initiated by light. So if it's kept in dark brown bottles, this is a deductive question. You're not expected to know this from the book. So when they say suggest, that means it's not on the spec, but there's probably enough information there for you to have a think about it. So that would be a reasonable thing to put. The next thing, now that you know that light actually might speed that reaction up, a potential safety issue, well, what's the reaction going to make? It's going to make oxygen. Oxygen is a gas. If you have a gas build-up in a sealed container, what's it going to do? It's going to explode, isn't it? The container is going to burst. So something along those lines would be appropriate to suggest. Okay, so let's now move on to the next question. So let's now go on to question number 2, which is on... So, looking at the question, it gives us an equation, which is here. And what we need to think to ourselves is what are the reactants and what are the products, because that's what we need to be able to do for Kc. Sorry, what I meant to say there was Kc equals the concentration of the products over the concentration of the reactants. So looking at our highlighted equation, we've got to identify what are the products and what are the reactants. So we can see that the PCl3 and the Cl2 are products, and the PCl5 is our single reactant. So we've got our first mark, haven't we? Because we've written the expression for the equilibrium constant, but it says for the Ford's reaction. So it's quite important to make sure that what we're doing is treating the reaction as moving in this direction. So the forward reaction is obviously left to right. So bearing that in mind, what we've got to do is to put in what the actual concentrations of products are. So what's the expression with that reaction in mind? So it's one thing to write out a general Casey expression, it's quite another to actually write out the Casey expression for the forward reaction that we've been specified to look at. So it should look something like that, and you need always to make sure that you're using square brackets. So the next thing to do is to put the numbers into that, because what they want us to do is calculate the value of the equilibrium constant Kc. And what's really important also is it's two significant figures. Now bearing in mind it's 1 mark, you either get all of that or none of it. So you need to be quite careful not to just go and calculate it, do a wonderful job of working it out, but then put your calculator value in that has about 4 or 5 decimal places. Make sure it's two significant figures. So remembering that the square brackets actually mean the concentration of the substance inside the square brackets in moles per decimeter cubed, you can see quite clearly that we've been given the values up at the top, haven't we? So 1.2 is for PCl5 and 0.70 for both of PCl3 and Cl2. So that's the value we get if we put it into a calculator, but don't forget, highlighted in blue there, two significant figures. Only 1 mark, so you've got to get it all right. So we need to change that into two significant figures, which gives us 0.41, of course. Okay, so now let's move the page up and do the rest of this question. Okay, so it says the yield of PCl5 decreases when the temperature of the system is increased. That's an extremely important question or sentence to read and understand. So the amount of PCl5 decreases when the temperature of the system is increased. If we go back up the page, we'll see that the actual reaction is PCl5 going to PCl3 plus Cl2. So just as a reminder, let's pop that in. So in other words, the amount of PCl5 goes down when the temperature of the system is increased. So what you've got to think to yourself is what's actually happening if the value of PCl5 goes down. What must be happening is it's being converted into PCl3 and Cl2. So therefore, when the temperature of the system is increased, this direction is favoured. So the forward reaction is favoured when the temperature of the system is increased. So if hotter temperatures favour the forward reaction, that must mean that the forward reaction is endothermic, which is one thing you can put in, because they ask you in the question whether the forward reaction is endothermic or exothermic. Well, I think we've just thought that through. So what we need to be careful that we're doing is not just saying whether the forward reaction is endothermic, but can you see where I've actually highlighted it as meaning? So meaning the forward reaction absorbs heat to oppose the change and increase the temperature. What I'm doing there is explaining my answer, because it's 2 marks. A lot of people got the first mark because they understood what was going on, but they didn't get the second one because they didn't properly explain what they were thinking. So always look to the mark allocation to tell you what to write or how much detail to go into. So the next one says, predict how the magnitude of Kc. Now magnitude is a word that describes a mathematical size of a number. Now, if you're a mathematician and you've been taking maths, they may describe it in a slightly different way, but to my humble chemistry mind, my understanding of a magnitude is the size of a number mathematically. Mathematically meaning the important train of thought here. So it says predict how the magnitude of Kc would change. To me, that means I have to explain it in mathematical terms. So Kc is a fraction, meaning it's got two components. A fraction has a top half, which is called the numerator, and a fraction has a bottom half, which is called the denominator. The Kc expression that we drew earlier has a top half and a bottom half. So they want you to talk about if the temperature of the system was increased, what's going to happen to the top half and what's going to happen to the bottom half. So in mathematical terminology, what's going to happen to the numerator and what's going to happen to the denominator. So let's try and sum up what I've just said in a little footnote at the bottom of the page. You'll see there's a bit of space, so I'm going to pop something in there so you'll see what I mean when I'm putting the answer in. So having now thought about it for a second, we can say something about this in a more mathematical way. Rather than just saying the equilibrium shifts in one direction or another, or Kc gets bigger, or Kc gets smaller, we need to say why it gets bigger and why it gets smaller. So we've already decided and established that the temperature of the system is increased, and what happens is that favours the forward reaction, which means that the numerator in the expression, in other words, all of this, so my numerator is all of this lot here. So all of that gets bigger, because that's the right-hand side. Oops, not like that, it doesn't. Like that it does. So if that's being favoured, and those numbers, the concentration of PCl3 and the concentration of Cl2 simultaneously are getting bigger, that means that whole top half of the fraction is increasing. That must mean that because the reaction is moving to the right, just to remind you again, up in the top right-hand corner, our PCl5 must be going down in concentration. So if the top part, the numerator, is getting bigger, and the bottom part, the denominator, is getting smaller, then that means that Kc itself must be going up in size. So the way you'd word this is in terms of the sizes and the change in magnitude of the numerator and denominator respectively. So you'll notice I've done more than just say that Kc increases in size, which is what many people correctly said. So you're not wrong to have put that down. It's just unfortunately the wording of this question requires a little bit more. Okay? Because the numerator becomes larger and therefore the denominator gets smaller. That's the explain your answer bit. So if you look at the way the colour coding has been done in the highlighting of the question, and the answers to those particular parts of those highlighted parts of the question are in the written answer I've just added. So sorry to have spent a little bit longer than I'd normally do about a 1 mark question, but it was quite a specific and pedantic question, this one. Although it's 1 mark, fair dues, it's 1 mark, but 1 mark can always make the difference between one grade and the next, can't it? So if you look after the single marks, as well as keeping an eye on the bigger marks, if you've got the time, have a think about some of the more difficult 1 markers as well. So now let's go and have a look at the final question, which is the one that tests out your ability in long answer question styles. So let's have a look at this before I go anywhere near answering it. So compound X is an unbranched organic molecule. Now you don't have to worry too much about the fact it's organic, because you can see from the data for the composition by mass, you can see it's got carbon, it's got hydrogen, and it's got oxygen. So that linked to it being organic. Well, certainly the carbon and the hydrogen linked to it being organic. And the fact it says unbranched, they wouldn't have printed that unless there was a reason for it. So if you see this in a question right at the beginning, if they give you a piece of information that might seemingly be irrelevant, and very small and not very big part of the text, tuck it away in your short-term memory and highlight it or underline it, because I bet you'll need to come back to it at some point. Okay, so I think when I do this question, what I'll be doing is dealing with each part of the question, but then bringing the page back up to this particular part that we see in front of us on the screen right now, because it's a wealth of information that we can use at various points. So, the first thing they want us to do is to calculate the empirical formula of x. So to do that, we need to use this basic premise of the percentage over the atomic mass. So my first step is to divide the percentage given by the atomic mass for each element. So you're allowed to round up or down accordingly. So what you're going to do first is to divide each of these by the smallest. So to divide them by the smallest, you've got to work out which is the smallest. So the smallest is going to be 1.35. So if I move them over here and divide each by the smallest, those are the numbers that I get. So that obviously gives me C4H10O as my empirical formula. So, moving the screen down a bit, the next part of the question says write the formula of the particle responsible for the peak m over z31 in the mass spectrum result. So the m over z means the mass over charge. You assume that in 99.9% of cases the charge is +1. So therefore the mr of that fragment, the particle, is going to be 31. So that would give us something along those lines. Okay, so the next part of the question asks us to name the compounds X and Y, explaining fully how the evidence leads to the identity of X and Y. So before I even start writing anything down, I need to think to myself, what does the question actually want me to do? You want to know the identity of X, the identity of Y, explain fully. And it says specifically to include in your answer how the evidence rules out other structural isomers of X which share the same functional group. So you can see I've slightly altered my subheading, the third one down, saying what structural isomers can X not be. So that matches the part that is highlighted in blue. And these match the part that's highlighted in red. So at this point, I'm going to ask that you make sure you've got the actual sheet in front of you, so we can make casual reference to it during this screen being up on your computer or your device, without me having to actually move the video back to looking at the previous slide. So, first of all, we look at the mass spectrum, or the m over z of 74. So it says that the molecular ion is 74. So that's our first piece of evidence. And that also equals C4H10O, which we worked out of the empirical formula. The next thing to look at, seeing as we're on the subject of the mass spectrum, is the fact our attention was drawn to a peak at 31, or m over z of 31. So we can put something down in our ruling out section. So what structural isomers can X not be? It can't be a tertiary alcohol, because an m over z of 31 rules out a tertiary carbon. Why would that be? If I was to draw out a tertiary carbon structure, you already have 4 lots of 12 before you even start talking about hydrogens. 4 lots of 12 is bigger than 31. So 4 carbons is going to be 48, which is greater than 31. So therefore, we cannot have this structure present. So So the next piece of information is that X can be oxidized. So therefore we can now rule out certain possibilities. We need to start looking at the infrared spectrum now. And the infrared spectrum tells us two things. So that tells us very strongly, the IR spectrum, that Y is going to be a carboxylic acid. So if it's a carboxylic acid, that means that what would oxidize into a carboxylic acid? So what would X be? X can be a primary alcohol or an aldehyde. So what we're doing is we're looking at what is the evidence for X and then what are we ruling out what it can't be. So we know it could be a primary alcohol or an aldehyde because that's the only kind of thing that would oxidize into a carboxylic acid, because you have two pieces of evidence for what Y is. So therefore, it can't be the primary alcohol 2-methyl-propan-2-ol, as we were told in the question, weren't we, that it's unbranched. So therefore, what we've got to do now is to think about what it could be. It can't be a ketone either, because a ketone wouldn't oxidize into a carboxylic acid. So in that sense, we're now sort of brought back to what it could be. Looking again at C4H10O, that means that the only thing that it could be is a primary alcohol with the formula C4H10O. So therefore X has to be butan-1-ol. So if X is butan-1-ol, because it's a primary alcohol with the formula C4H10O, then X, which is a carboxylic acid, Y, which is a carboxylic acid, must be the carboxylic acid that butan-1-ol would oxidize into, meaning Y would be butanoic acid. So hopefully you can see that during my answer to that part of that question, I put several sections on my space and I could populate them as my thoughts started to tell me what I was leading towards. It doesn't mean you have to technically fill in this part first, followed by this part, followed by that part. What it means is you can go back and forth between them as you start to realise the pieces of the puzzle are fitting together. So let's have a look at the final part of the question and the final part of the test. So the last bit says, isolating pure organic product from its reaction vessel after synthesis often involves the use of a separating funnel, followed by the addition of an anhydrous calcium chloride. State the purpose of both of these steps. So what you've got to do is basically think back to our organic synthesis work and decide what each of those things actually does. So our separation funnel separates immiscible liquids. If you haven't come across the word immiscible before, it basically means cannot be mixed. So it doesn't exactly sound too different from the word immixable or immixable. So immiscible means cannot be mixed. Now you've done a practical on organic synthesis that included a clip by one of our technicians on the use of drying agents. And they used calcium chloride, anhydrous calcium chloride. We generally use anhydrous salts because the word anhydrous means that the water of crystallization has been removed. So they're going to tend to want to grab onto any water they can find to try and restore their water of crystallization. So they're good drying agents because what they can do is remove water from what we call a wet liquid. A wet liquid is a liquid that isn't water but has a little bit of water mixed in with it that you don't want. So you can't dry out the water in the same way that you'd hang up a tea towel, for example, to dry out in the sun. What you've got to do is use a drying agent, so chemically the water is being removed. So the anhydrous calcium chloride is a drying agent that chemically removes any water that we can't physically remove by any other means of drying. So we call the anhydrous calcium chloride a drying agent. I've written in the little notes in purple just to try and explain a little bit about why I've put those answers in the way that I have. So it doesn't mean you have to give an explanation about it chemically removing water, but if it helps you remember why it acts as a drying agent, think of the anhydrous aspect of the calcium chloride. So it doesn't have to be calcium chloride, it could be magnesium chloride or anything like that. We generally use group 2 chlorides. So the anhydrous aspect means that the water of crystallization has been removed. So that means that the salt, the anhydrous salt, is going to want to try and get some water crystallization back to help it form its crystalline structure. So thinking back to our work on water crystallization. So it chemically removes traces of water by using that water to restore its water crystallization. And it can even do that whilst it's under the surface of another non-aqueous liquid, such as cyclohexane or hexane, for example. So if we were to have some wet hexane, and that wet hexane had some anhydrous calcium chloride dropped into it, what you'd do, if you remember the clip that you would have watched in class, is give it 10 minutes after shaking it. So you'd obviously put a stopper in the top of the bottle, the container, and give it a good old shake. And then 10 minutes later, what would happen is your hexane would be dry. And you'll have a hydrated calcium chloride. You'll see that the calcium chloride is now taken on some water. But the important thing is that the hexane is actually now dry, so the hexane can be poured off, leaving the hydrated calcium chloride behind. Okay, so hopefully you found this walkthrough reasonably useful, and a little bit at the end about the use of drying agents, just to clarify things, hopefully would have been helpful as well. Thank you for your time again, and obviously don't forget to keep in touch with us via email, come to one of our subject extensions, and ask for any help you need next time you're in college. Okay, thanks a lot. Bye.